Go ahead, Jean-François.
Okay. So let's start. So with Claire Moutou, we will present a quick overview of the SLS SPIRou Legacy Survey and SPICE LPs with SPIRou. So behind the two LPs, the Science Consortium gathers about 80 PIs, mostly from co-Is, in fact, mostly from France and Canada. And we usually regularly meet in science workshops at various years. For instance, last year in 2023, in fact, in Château de Mons in southern France. So it started with the SPIRou Legacy Survey, the SLS, that got allocated 310 nights since 19A to 2022A, albeit with a slow start for various reasons, including COVID-19, before mid-20A. After that, we got SPICE, that ended with a PI program in 24B that got allocated 206 nights over 5 semesters, so up to 24B. Altogether, and thanks to the efficiency of the CFHT QSO team, we got 480 nights of validated data, plus 52 nights of lower quality data for the pre-mid-20A data. And all this effort was focused on two main science goals. First, the planetary systems around nearby M dwarfs. So the idea was to detect and characterize these planetary systems, and at the same time to model and filter magnetic activity to optimize the detection and characterization of the planets. So it was split into two flavors, in fact, two work packages. Work package 1 that was dedicated to a blind planet search around about 60 nearby M dwarfs, and then WP2, who was focused on the study of 45 M dwarfs with transiting planets this time, so a different sample. Transiting planets detected with tests and for which we wanted to have mass measurements, accurate mass measurements. And the second main science goal was about the impact of magnetic fields on star and planet formation. The goal is actually to try to detect the large-scale magnetic topologies of these pre-main sequence stars, and also the accretion patterns on the surface of these stars, and also to look for potential young close-in planets, giant planets orbiting these stars. And the sample was about 60 class 2, class 3, and class 1 low-mass PMS stars. So just very briefly, at the outer SPIRou, we have a high-resolution near-infrared cryogenic spectrograph collecting the full domain from 0.95 to 2.5 micron in a single exposure at a spectral resolving power of 70K, and yielding a peak signal-to-noise ratio of about 100 per pixel in a 1-hour exposure on an M dwarf with the H magnitude of about 11. Velocimetry-wise, we're able to get RV precision of about 1 to 2 meters per second RMS on a timescale of years, and that was thanks to the tremendous effort of the SPIRou DRS team, in particular the SPIRou pipeline and the line-by-line technique of measuring accurate radial velocities, all detailed in these papers here. And of course, there was spectropolarimetry, so measuring and detecting circular and linear polarization in line profiles so that we can study magnetic topologies at stellar surfaces. Just very briefly, so here is a raw SPIRou spectrum. You see the orders side by side here. When you extract these orders, you get something like that with lots of lines, stellar lines, of course, but also telluric lines. Telluric lines not just between bands, but also within bands. This is, for instance, a zoom on the CO banded region where telluric lines and stellar lines mix horribly together. And this is why we really have to have an accurate, very powerful pipeline to be able to remove telluric lines and get radial velocities from the stellar lines. And now I'll just let Claire present the WP1 and WP2 results.
Yeah. So in the first science work package, we were actively searching for exoplanets around nearby M dwarfs with the radial velocity method. So why do we want to observe these stars in particular? So M dwarfs are the most numerous stars in the galaxy, and especially in the solar neighborhood. Yet only a fourth of them have their planetary systems really known. So it's really important to go and fetch for these planets. The problem is that the planets around these stars get smaller, and the systems get multiple when decreasing the stellar mass. So it really requires a very high precision to find these planets. And we expect from transit surveys 1 to 2 planets per star at an orbital period of less than 100 days, which include the habitable zone of these stars. So it's very important, it's very challenging, and we really want to go for the mass measurement with the radial velocity method. So from SLS to SPICE samples, what we did is to decrease the stellar mass of the sample, to have the most obvious view of the full solar neighborhood with this type of stars. So SPIRou is optimal for this M dwarf. The first reason is that they are much brighter in the near-infrared than in the optical. The radial velocity content is also larger because we have all these bands from molecules in the near-infrared. And finally, stellar activity is expected to be damped at longer wavelengths, and it's exactly what we have been observing as well. Next. So to jump to the results in only the last year, but it took us some time to figure out how to really go to this precision. In the last year, the harvest was of these 4 planets. There are stars in the neighborhood for which no other means had found any exoplanets. And this includes in particular a very close by binary star, list 725A, which has a hot super Earth and found by a postdoc, Pia Cortes, last year. Then we found a flavor of these specific planets which are in between the Earth mass and Neptune mass, so super Earth or sub-Neptunes. And this is from hot ones with 6 days period to very cold ones in 100-day period. And the last example I would mention is the Gliese 410, which is the last one which was published and accepted, which shows a very secure 6-day planet signal, and potentially 2 other planets in a resonant chain. So very exciting in terms of dynamics. So if we put these planets in a plot, mass versus orbital period, the red points are the one I just mentioned, the new SPIRou planets. The open circles are the ones known from the literature, which mostly are also nearby, also M dwarf, but not nearby, found by transit surveys mostly. And the navy blue are known planets for which we also have a good time series with SPIRou. We decided to observe these planets even though they were known, because with additional measurements we can find whether the planet is real or not, if it's not chromatic. We can refine the ephemeris and mass measurements, and we can also search for the planets in the system. And the light blue, and the light blue symbols are the candidates, which are not mature enough to be published yet, but very good candidates, and we maybe need more work or more data, it depends, to finish them. Next. So why is it so difficult? We are aiming at the meter per second level, and so at this level everything counts. And as we've seen from the beginning with SPIRou. And the last problem, which took us years really to figure out, is the very small, tiny residuals of telluric contamination at the level of 1 or 2% maybe, which are not common to all stars because it depends how fast your star goes versus the Earth's velocity. And then we had to spend a lot of brain time and also dedicate full PhD on this matter to find the correct way to get rid of this small contamination. So if, for instance, next plot. So this is an example where we see a known planet. On the left, that's raw SPIRou data, already very stable, but not stable enough, because as you see, the Fourier analysis shows a very strong peak at a 1 year period, which is very, very suspicious. And so when you apply this weighted PCA analysis, you get rid of this systematics and you find the exoplanet signal at 15 days as expected. So the next thing you need is to have a dense sampling to really be able to look at all the signals in your time series. And then you can use ancillary data. I will show that later. And after this many development, we can reach really, and we have now robust detection limits at a level of 1 meter per second. Next. Yeah, next. And this is the last example, which is just submitted at the moment, but not yet accepted. It's a system with 2 planets with a semi-amplitude of radial velocity between 1 and 2 meters per second. But as you can see, the error on this semi-amplitude is much less. It's 0.3 meters per second only. And one of them is in the habitable zone of its star. It's a very nearby star, so it's a very interesting system, the ones we were aiming at. And we finally found with this huge number of visits. As you could see before, the number of visits per star is about 200 to get this very tiny signal. It's the same order of magnitude as what is done on HARPS or other radial velocity facilities. You really need 1 week per planet, I would say, as an effective telescope time. That's what's needed. Next. So in addition to observing in radial velocity, we have circular polarization. And that comes in 2 flavors. You can have you have the circular polarization, which gives you the large scale magnetic field, and that's an example where even very slow rotators in this kind of low mass stars have a very strong signal. And as you can see here, it's a time series of the longitudinal field observed, so the large scale field. It evolves with the rotation of the star, but also quite fast from 1 year to the next, which is probably an indication of the polarity switch of the star, which happened in all magnetic cycles. So that was really a very good, nice byproduct, especially when you know that in the habitable zone, we can expect the magnetic field of the star to have quite an important impact on the atmospheric erosion or habitability of the star. Next. And also in the intensity spectrum, you can measure the small-scale magnetic field. And then that was also developed by one of the PhD students in our team, who find a way to measure that on all and every SPIRou spectrum, and found the evolution of this small-scale magnetic field. So that's one of the highest magnetic field in our sample, EV-Lac. It's a medium dwarf with a rapid rotation and a magnetic field between 4 and 5 kilogauss. And what you can see, the rotational modulation of these active regions. And in the sense, it's known to be one of the best proxies for radial velocity jitter, so it's very important to measure this quantity, and that's now done routinely. Next. So to stay on EV-Lac, EV-Lac is very active, so it's a benchmark to try many things, and it has been observed together with SOFI and optical and SPIRou in conjointly. One other PhD student in Grenoble has found out that while in the optical you find a radial velocity RMS of 90 meters per second, in the near-infrared it's only 7 meters per second. I think Arthur was shown this morning. And he found out that it was related to the contrast between the active regions and the photosphere of the star, which is extremely chromatic and with expected power law. And that's exactly what we see in radial velocity. So that's another way of looking at this. And you can also use these contrast measurements to measure and correct for this radial velocity jitter. Also in the near-infrared, it's really, really low. Another way to look at this was to measure and identify. You can show the plot. So identify lines which are sensitive to the activity. So here it's a machine learning classification of lines measured individually, where you see these clusters in blue, which are really showing the lines which are sensitive to activity in the near-infrared, in the SPIRou domain. And there are very few, actually just a few hundreds of them, while we have thousands which are not sensitive to activity. So all these together start to show that we can really try to look for planets even in very active stars. So next. Yeah. And the second science work package, WP2, is aiming at looking at transiting exoplanets. So transiting exoplanets are found by space photometry, at the moment by TESS mostly. And it's a benchmark for future mission Plato, of course. So radial velocity observations are needed to establish the nature of the planetary signal, and also to measure the mass and eccentricity, while the transit will measure the radius of the planet and the orbital period. So both together gives us a lot of information. So with WP2, we have observed 45 stars in this matter. This is just one example. So TOI 4860, while most of the targets we've been observing were aiming at a radius gap between the super-Earth and sub-Neptunes, this one is a closing giant planet orbiting an M dwarf. So it's not expected. These systems are extremely rare, and the core accretion model is not expecting these planets to be able to form around M dwarfs. But SPIRou has confirmed a 0.27 Jupiter mass planets in orbit in a 1.5 day period. And in addition, by looking at it for as long as possible with the instrument, we were able to find the possibility of another planet in the system with a much longer period, which only SPIRou has found so far. So it's probably not complete enough on the orbit to be completely established as a planet, but we will confirm it soon. I think I'm done.
Yeah, that's clear. And now let's switch to WP3. So studying magnetic fields and star-planet formation. So the goal is to first start with studying the magnetic fields of the stars themselves, so the low-mass PMS stars, and to investigate how these PMS stars accrete from and interact with their planet-forming disk. So here is a picture of what happens, in fact. So you have the star in the middle with its magnetic field in red, and the slimy greenish material all around is the disk, the inner regions of the accretion disk, with material flowing onto the star through discrete accretion funnels following magnetic field lines. And the whole goal is to understand how these things work in practice. So we also want to look for closing giant planets orbiting PMS stars, essentially in the inner regions of the accretion disk. So for instance, one of them, GMOIG, it's a classical T-Tauri star, 2 mega-year old, that's been observed within the multi-instrument, multi-program Ulysses campaign, and that we also observed with SPIRou and within the SLS and within SPICE. So this is a work done by Bonnie Zahir and collaborators. So we detected the magnetic field. These are longitudinal magnetic fields measured from circular polarization data, from Stokes V data in various SPIRou runs here. And fitting this data with a quasi-periodic Gaussian process, we were able to not only detect the field, of course, but measure a very accurate rotation period, use these Stokes V profiles to map at various epochs the large-scale magnetic field of the star. So we show here the reconstructed map with Zeeman Doppler imaging, the three components of the field in spherical coordinates, so radial, azimuthal, and meridional magnetic field. And in this particular case, we've got a strong poloidal field with a 3/4 of a kilogas dipole at the surface of the star. We're also
Excuse me, can you begin to wrap up, please? Thanks.
Okay. I'll just finish the slide here. So we also measured radial velocities from these PMS stars, so filtered out from the activity. And for instance, in that particular case, we see a periodic variation suggesting the presence of a candidate 1.1 Jupiter mass star orbiting at a distance of about 0.08 AU, so within just the inner regions of the disk. So we got similar results from other class 2 PMS stars. We also got similar results from a class 1 semi-embedded protostar. I will just skip the result because I just don't have time, obviously. We also got similar results from class 3, so the older stars that for which the accretion disk vanished. And this one, for instance, V1298 tau, hosting well known to host 4 transiting planets. So we detected the field again, varying on short time scales, reconstructed the magnetic maps, also showing fast temporal evolution, measured radial velocities again, measured the contribution to radial velocities of the 4 planets, detecting planet E, the outer planet E only. Hence, we only got upper limits. And in particular, that plot showing that in a radius versus mass, so planetary radius versus planetary mass, some planets are born with the mature densities fairly early, a few grams per cubic centimeters. For instance, this is the case of planet E, the outer planet E here, while some do not actually are born with the inner ones are born with a much smaller densities. And this is the same for Eumic, for which the outer planet, Eumic C, has a density about an order of magnitude larger than the inner planet, Eumic B. So these are just examples of the results we obtain within the SLS and SPICE. So altogether, we have 60 published refereed papers, 40 of them since 2023, which shows the need for the full temporal dimension to be for the data to be optimally exploited. High impact results as well, despite recent publications, a very decent H index. All these data are from ADS directly. Another 10 papers submitted or about to be, and we expect another 30 or so papers in the coming 2 years. And a number of papers also with purely legacy content, for instance, on spectral modeling of M dwarfs that has implications much wider than the SLS and SPICE themselves. So just to wrap up, a very productive high-impact science with the SLS and SPICE. 70 papers published already, 30 more to go on all the on the 2 main science goals plus papers with legacy dimension. We are now running the Planets LP. It's ongoing from 25A to 26B. Possibly a follow-up in 27A as well. This time we include a 4th WP, an exoplanet atmospheres. This is what Florian talked about this morning. 240 nights allocated, 35 validated so far, and later on, further away from now. So we have the Amaki community survey that is proposed by Claire Moutot, and for which we'll have a talk tomorrow, addressing all WPs plus additional topics, an even wider LP. So yeah, that's
Yes, thank you very much. Very productive program.